All right, welcome to day 2 of CPP. It's my pleasure to kick things off by introducing Jennifer Paykin as our second keynote speaker. Jennifer received her PhD from the University of Pennsylvania in 2018, and she's worked on a number of topics from domain-specific languages to linear types, and is perhaps best known for her work on quantum programming and logics for reasoning about quantum programs. She's worked both in industry and in academia. She worked at Galois and then at Intel, and is now an assistant professor at the University of Vermont. And I'm delighted to have her here today. Welcome.
Thank you so much. Thank you so much. Thank you for the introduction. Thank you to all the organizers for inviting me. Really happy to be here and tell you all a little bit about verification of quantum programs. Is the volume in this okay? Okay. Good. So I wanted to start off with a little bit of a workflow. If pretending for a minute that you are a quantum engineer implementing and running an algorithm on a quantum computer. What does that sort of thing look like? So first of all, you are not writing your algorithm in an ordinary classical, what we call classical programming language, since your quantum algorithm uses quantum-specific operations and abstractions. So we're going to use some kind of quantum domain-specific language. So here, which you should not be able to, don't worry about reading, but like here I've written something in Qiskit, which is a quantum computing library embedded in Python. But there's lots of other quantum programming languages that exist and support slightly higher level or slightly lower level features. We had a whole workshop about it yesterday, Planck. But I will say that almost all of these quote-unquote higher level quantum programming languages are going to be compiled to some kind of intermediate representation, which we typically think of as quantum circuits or something in the quantum gate model. So these circuits are not circuits in the hardware sense, but they're basically just sequences of primitive operations applied to qubits, the quantum bits. So the idea is that these gates correspond to primitives supported by real quantum computers, which do in fact exist. Sometimes we have to clarify. They're not quite useful for real-world applications quite yet, but there's been a lot of really exciting progress in terms of building these machines that we've seen just in the last few years. But our quantum computers of today not only are small, so they're on the order of like anywhere between 10 to a few thousand qubits. They're also extremely noisy, so they introduce a lot of errors. They only support like short-lived execution times, coherence times, and they have other constraints depending on the underlying technologies. So in order to actually run our quantum circuits on these devices, not only do we need to compile them to circuits, but we also need to apply optimizations, make the circuits as small as possible, but also obey the constraints of a particular quantum device, such as layout, placement, things like that. And another example of a type of transformation pass is something like an error correction pass, which enables us to adds layers of detecting and correcting errors that are introduced by these devices. So alternatively, if the circuit is small enough, then you can simulate it on a classical, in a classical program, a classical simulator. But of course, by definition, general purpose simulators like that scale exponentially with the number of qubits. So this can only be done in small cases. And so for example, the best simulators right now might support 30 to, at the maximum, I think 60 qubits. And that's all that they can simulate. Okay. I want to note also that executing a circuit on a quantum device is not like a one and done deal, because quantum programs are inherently probabilistic, not to mention all the noise introduced by the devices. You are going to need to execute your circuit run a bunch of shots. So it's like hundreds to up to like millions of shots per run. And then the output of this is a probability distribution of measurement results. Okay? And of course, that's for like a single instance of running your algorithm. And plus, I will point out that the quantum computers of today are expensive to use. A lot of them are available via the cloud, which is great. I think the public cost of cloud time on like one of the IBM devices is somewhere between $50 to $100 a minute based on the plan. Right? So the question that I have for you is the typical motivation of formal verification of software systems. How do you know that your quantum program is doing what you think it should be doing, right? I'm sorry to report that the state of the art in industry is manual analysis, pretty much. You as a user are going to compare these probabilistic results against what you expect them to be. Maybe you have, a specific probability distribution that you are expecting, and you're going to analyze whether what you got out from the device is like close enough to what you were expecting. And so if they match, then great. And if not, then there's very little to tell you where the problem came from. Like the problem could be in your implementation itself, of course. Or it could just be a problem with your expectations. So maybe you're not correctly accounting for the error models of the device that you ran this on. Perhaps there's a bug in one of the optimizations that you ran, or maybe the optimizations are just inefficient, and then they compound like the approximations that are introduced by some of these optimizations in a way that skews the measurement results. So I'm showing you this workflow, like not to criticize, but just to give a glimpse into the value of formalization and verification in these quantum systems. So my goal for this talk is to reflect on some of these circumstances and point out some of the open questions that exist in the quantum formal verification space. I'm not going to do a totally comprehensive survey of the literature, but I will point out especially some of the projects that are being or have been presented this week, because I think that's a nice tie-in. So with that, for the rest of the talk, we're going to follow the following outline. We're going to start with a basic overview of some of the math of quantum circuits, just to sort of get a foundation on that. And then we'll go a little bit deeper into a few different verification techniques. And sort of highlighting some of the pros and cons of different approaches. And then we'll wrap up. So that's like high-level overview. Before we start, though, I actually want to start with step 0, which is a little bit of a vocabulary lesson. So when I say formal verification, and probably when a lot of you say formal verification, I'm thinking about something like machine-aided mathematical and logical methods that I'm using to prove that some program matches its specification, or maybe in the case of like hardware formal verification, to prove that a system matches a formal verification, a formal specification, right? But if you go and talk to a physicist and you talk about verification, there might be a mismatch, because they might be thinking about quantum verification. I'm not 100% positive on where the boundaries between all these phrases lie, but generally, quantum verification will refer to the idea that a quantum experiment or a system or like computer actually demonstrates quantum behavior that can't be achieved in a classical way. So this is a really interesting like theoretical question of, is this thing quantum? And then of course in the quantum space, we're also talking to a lot of engineers who are maybe building quantum computers. And so then there's like also a mismatch between formal verification, as I'm thinking about it, and maybe a broader perspective on verification, and like in terms of like verification and validation, where verification can refer to formal verification, but it can also refer to just like other methods for asserting that some system matches a specification. So simulation, testing, things like that. So it's when working in these interdisciplinary fields, as I'm sure a lot of you know, it is really important to like get on the same page, and that can even start with language. Okay, so let's talk a little bit about quantum circuits. So here I have the picture of a quantum circuit that we saw before, and it's made up of, as I said, qubits, which are represented by these wires, the horizontal lines, and then gates, which are like primitive things that a quantum computer can do. So let's start with qubits. Mathematically, a qubit can be represented, the state of a qubit can be represented as a superposition of bits. So a single qubit is a superposition of the 0 bit and the 1 bit. And this syntax here, if you haven't seen it before, this like half bracket around the 0 and a half bracket around the 1 is pronounced ket. It's like the right-hand side of a bracket. And that's just referring to like the classical basis state corresponding to 0, classical basis state corresponding to 1. When I say superposition, I mean that this is a complex linear combination of the 0 and 1. So alpha and beta here are complex coefficients, and they satisfy this property that if you take the norm of alpha and square it and add the norm of beta squared, you get 1. And like, I think this is, you can kind of think about this constraint very, very roughly as this is almost like a probability distribution. And in fact, when you take a qubit and you measure it, what you're doing is effectively sampling from that probability distribution. So if you have a qubit in this superposition and you measure it, you're going to get out the bit 0 with probability norm of alpha squared, the bit 1 with probability norm of beta squared. So where the power of quantum systems, a lot of it comes from, is when you have not just a single qubit, which is a superposition of 0 and 1, but multiple qubits, where if you have n qubits, your quantum state is a superposition of all 2 to the n bit vectors of length n, right? So in the 2-qubit case, that's a superposition of 0, 0, 0, 1, 1, 0, 1, 1. Right, so this like 4-qubit system here is always going to be represented by 2 to the 4 sized vector of complex numbers. Okay. So we talked a little bit about qubits, we talked about measurement. Let's talk about these other operations, these what I'm calling unitary gates. And the semantics of these unitary gates is a complex matrix, so its action is going to act on these state vectors. And the condition of being unitary says that it has an inverse, and its inverse is its own conjugate transpose. So it's like easy to compute the inverse from the matrix representation. Okay. So this is sort of a very like first day semantics of quantum programs. Okay. And you know, there's this is kind of leading us to the first like open problem that I want to point out, which is like, how do we represent this semantics in a way that is scalable, sort of, and suitable for verification enough? So like the first option is vectors and matrices. This is very, commonly used. And because we can, take advantage of existing structures for reasoning about linear algebra, things like high-performance computing, computational linear algebra. One downside is that these are, complex vectors, and so, I can tell you from experience that floating point numbers are not precise enough to capture the semantics of non-trivial algorithms. And of course, also, this is definitionally not scalable, so a state of n qubits requires a vector of size 2 to the n. So are there any other options? Well, of course there are. Oh, what happened there? So I'm going to just highlight a few creative representations. So one is the quantum decision diagram, which represents a linear algebraic structure like vectors and matrices as a graph, and that allows us to repeat subterms and shared nodes. And so in the worst case, the complexity of a quantum decision diagram I don't think is any better than the corresponding matrix, but in practical cases, it can be quite a bit better. Here's another example, which is the phase polynomial representation, which encodes operators like Cliffords and measurement as maps from the basis state, like x, so this is on the right here, to an algebraic formal sum of other basis elements, so that's a sum over y, with some coefficients. And so the phase polynomial representation, one, looks like a math equation, which is really nice for working with mathematicians, but it's secretly a formal structure that can be simplified and transformed according to some well-defined rules. And furthermore, because these symbolic variables, and in fact all the components in the underlying formal structure are just bits, it's actually really well suited for automatic equivalence checking with S&T solvers. So really, this good choice, phase polynomials. Here's one more representation that I'd like to mention, which is the ZX calculus, or the ZX calculus, which is a categorical formulation of quantum states and operators. So this is a diagrammatic representation, which means that states and operators are represented as diagrams, which correspond to very, very closely to morphisms in an underlying category. And equivalences in the calculus are represented really nicely in pictures. So it can be nice to work with on paper. So equivalence in the ZX calculus is not tractable in the general case, again, but a lot of work explores how to build tractable subsets of rewrite rules and heuristics for diagrams of particular shapes. Okay, so with that, I want to go a little bit. Let's start talking about verification. Right, we've talked about representations, we've talked about semantics. Let's talk about verification. And to sort of introduce this idea, I want to use a particular line of work, which I'll refer to as Inquire, because that's the name of the GitHub repository. So this is work that I was involved in early on, but since then has taken off under the direction of Robert Rand and a whole bunch of other collaborators. So Inquire and its first iteration, which was Quire, is a system for formally verifying quantum programs in Rock. So let's start off with a simple example. So here we have a simple quantum circuit defined in Quire with the sort of diagrammatic circuit on the right-hand side. And this is a very simple operation which prepares a qubit in the 0 state, and then it applies the Hadamard gate, which sort of puts it into superposition, and then applies a measurement. And so the result of running this circuit should be 0 with probability 1/2, and 1 with probability 1/2. So the question is, well, how do we specify and verify that this is the behavior of the coin flip circuit? Okay. Well, I'm sorry to say that the simple semantics that I showed you like 2 slides ago is not the semantics that we're using in this situation. And the reason is because that requires probabilistic steps. Certainly, we all have lots of techniques for reasoning about probabilistic systems. But one technique in the quantum space is actually sort of a nice way of moving around this. And so not only is this nice, but it's also the way that physicists and mathematicians think about quantum computing in generality in many cases. So rather than qubits being represented by vectors and operators like unitaries being represented by matrices, qubits are now going to be represented by a matrix itself, which is called a mixed state. And what a mixed state is essentially is a probability distribution over the pure states, so over these kets. So this is just like the usual trick of changing a probabilistic step relation into a relation, a deterministic step relation over probability distributions, but done in a way that can sort of like combine all of the probability distributions into one matrix. So rather than matrices as sort of the semantics of unitaries and measurement are these specific kinds of maps on these mixed states, which are also called density matrices. And we can have a deterministic step relation rather than a probabilistic one. So if we look at this specification of the probability distributions of this coin flip circuit, as a mixed state, we can represent it as this following matrix. It's a probability distribution, 1/2 being in the state 0, in the pure state 0, 1/2 being in the pure state 1. And so this is the representation that we use like directly in Rock, using nice notation tricks. We sort of say that the semantics of the coin flip circuit produces this particular mixed state as the output. And the proof, while written shortly right here, does applies a bunch of custom tactics that do matrix manipulation in Rock, which, as you might imagine, takes a little bit of finessing. But the tactics, Robert has built up a very nice library that can do quite a lot. Okay. So this approach of reasoning sort of directly about the semantics of quantum circuits can get you pretty far. So another use of this sort of approach is Vox, which is a verified optimizer for quantum circuits. This is a paper from 2021 by Kesha Halada and Robert Rand, and some others at UMD. And so this is in this workflow, this is a verified optimizer, right? So it's able to take equivalences of circuits, verify their correctness using this semantics, and it also has verified like other kinds of optimization passes, like hardware-aware passes for circuit mapping, layout, routing. So fully optimized verifying compiler. Fully verified optimizing compiler, that's what I should say. Okay. So with that said, we're skirting a little bit. I'd like to bring up this open problem number 2. So far, I've talked about quantum circuits, but at the very beginning, when I was talking about this workflow, we had a difference between quantum programs written in some domain-specific language and the quantum circuits they compile to. So in addition to the quantum gates, these quantum programs have a bunch of things, like they might have interleaved classical and quantum computation. They might have classical control flow, like loops. Certainly higher level quantum abstractions, and even things like parameterized circuits in terms of, or parameterized programs in terms of like the number of qubits that are the input, or some rotation angles, things like that. Perhaps surprisingly, expressing the semantics of these quantum programs compared to quantum circuits can be quite challenging. Because of the mathematical foundations of the quantum circuits don't, by themselves inherit the structure of the classical computations. So one evidence of this is a great line of work on the protoQuipper family by Neil Ross and Peter Selinger, among lots and lots of others. But I'm pointing this out because in terms of formal verification, this is really important. We don't just want to verify a quantum circuit on its own. We want to know what the overall algorithm is doing that might call out to these quantum circuits or interact with them in non-trivial ways. So additional evidence that this is an important problem is all of these papers papers and talks that we've had this week focusing on verification of programs rather than just circuits. So here's an example that touches on just a little bit of this problem. So here we have a circuit. This is an example in Squire, which is one of the follow-on languages following Quire, a simple quantum IR. So here we have a description of a parameterized circuit. So this is the quantum Fourier transform, which is defined on any number of wires. So any number of qubits. And so because we're working in ROC, we can simply define this as a function from natural numbers to circuits. So this is kind of like a cheat code for integrating classical parameters with quantum circuits. And so the result that we could get out is a lemma that says, okay, for any number of qubits, right, if you interpret this circuit as a unitary and you apply it to an arbitrary basis state, x, what you get out is the following pure state, which is the usual presentation for the specification of the quantum Fourier transform. Okay. So the specification is pretty readable. And why I call out this example is the part that's probably not interesting to most of you, which is that this property holds for any number of qubits at any basis state, right? Because that's the way that we prove things in interactive theorem provers like ROC. But this is the part that consistently impresses physicists and engineers with whom I share this idea. The fact that formal verification is not limited by the scalability of the number of qubits in the generic case is consistently mind-blowing. So I just like to throw that out there. So this is a concrete value to quantum computing developers. So of course, there are a lot of trade-offs to doing formal verification using ROC or other interactive manual theorem proving tools. So trade-off number one is the trade-off between the powerful reasoning techniques that you get with the fact that requires a lot of expert knowledge, proof developers, and relatively limited automation. So this is, as always, a very important discussion, and there's lots of work, pushing for more automation. There's work that's pushing for being able to capture these more powerful reasoning techniques with more automated interactions. So a lot of really interesting work going on there. Another trade-off, is about the way that we express specifications. So if you're thinking about proving that two circuits are equivalent, that's a specification that's very easy to understand. That's easy to show somebody and say, this is what this specification means. If you're looking at a specification that says this circuit transforms this density matrix into this other density matrix, that can be harder to interpret. So I think open problem number 4 is, how do we actually express specifications in a way that is formal, readable, intuitive, and well suited for formal verification? This is also a problem that a lot of people are actively working on. It's really interesting ideas. I'm just going to point out yesterday the keynote at Planck by Christoph Charton was about this very problem using path sums, using the path sum representation. So one more trade-off that I want to point out. There's, of course, lots of really interesting, it's important to capture not just functional specification of these quantum programs, but other kinds of properties. So one example is after you've gotten to a certain point of the program, are these two qubits entangled or are they disentangled? Is this qubit restored back to the 0 state, which is something that you need in order to use ancilla properly, and so on. So this is a point in favor of having really powerful expressive reasoning principles, such as in ROC. But there's still a lot of kinds of properties that require more work and effort. So things about probabilistic algorithms, when we talk about the interaction of classical and quantum data, we sort of have to go beyond the mixed state formalism that I described before. And so the best way to do that, that's definitely an open question. And also when we want to reason about errors, such as the errors introduced by quantum devices. This is a really important point of discussion. So there's been a lot of discussion about that this week as well. And that question about errors is what I'm going to focus on in this next little case study. Specifically, I'm going to talk about a paper that I contributed to, but was definitely not the primary contributors. Specifically, the primary authors, Qin Chen, Yuhao Liu, and Guxu Li at University of Pennsylvania. So the goal here was to verify error correction, but more specifically fault tolerance. So let's give a little bit of a scope to this problem. So as a reminder, error correction can be thought of as this circuit transformation to protect us from errors that occur on the quantum devices. And this is really important right now, specifically because just in the last few years, we've seen the first demonstrations of successful error correction on real devices. So we're getting to a point where these quantum computers can actually handle doing some error correction, which is a really important step. So here's a very, very high-level overview of quantum error correcting codes, QECC. So similar to classical error correcting codes, we're going to be embedding a logical qubit, so that's this like input on the left here, into a larger code space. So there's some sense in which we're like duplicating information to distribute the information of the logical qubit among the larger code space. I won't get into the mathematics of how that works exactly. But the idea is that once you're in this code space, once you're in this larger space, if an error occurs, there is a procedure to do some kinds of observations and computations on the state space that doesn't change the state, but does output some classical bits, which is called a syndrome, that tells you if an error has occurred, and depending on the code, what error it was and how to correct it. Okay, so once you have that sort of syndrome information, you can potentially apply an error correction, which reverses that error that occurred and brings you back to the state that you were in before and brings you back into the code space. So we also want to be able to do operations on this code space, which act as though we had done them on the logical qubit from the beginning. But we want to do those operations on the encoded space so that at the end, we end up in another state in the code space. So in the last few years, we've seen some really interesting efforts towards verifying quantum error correction codes using automated techniques like SMT solvers and symbolic execution. And this has been quite successful, I think, in large part because many quantum error correction codes are built out of a well-behaved subset of quantum operations called the stabilizer formalism. So if we look back at our different possibilities for semantics of the language, we saw pure states and mixed states. The stabilizer formalism is an alternative, which only applies to certain kinds of operations in the quantum space. But rather than vectors of exponential size or matrices of exponential size, states are now represented by a set of Pauli operators that stabilize the state. Okay, so what's going on here? So a state is characterized by the set of some operators S, such that when you apply that operator to your state, it doesn't do anything. It stabilizes that state. And these operators are drawn from this Pauli group, which is a very well-behaved subset of unitaries, which I don't have the definitions on the screen, but one thing to note is that the Paulis can all be represented by bit vectors themselves. Okay. So each Pauli operation can be represented by a bit vector. And this stabilizer set is actually always going to be a group, so you only have to record the generators of that group rather than the entire thing. And the operators that act on these stabilizer states can be described in terms of what's called a tableau that basically describe how you transform the generators of that Pauli group into other Paulis. So like you're basically mapping this function over your set of generators. So because this tableau is just talking about sets of Paulis, that can in and of itself be represented as a bit vector representation. So ultimately the story is that all of these things, the stabilizer formalisms, can all be reduced to bits. And furthermore, not that many bits, because instead of having exponentially many complex numbers, we only have something on the order of n squared bits in this representation. So the stabilizer formalism is actually efficiently simulatable on the classical computer, which contributes to the fact that we are able to analyze it using classical analyses in a pretty efficient way. So that's error correction. Certainly, verification of error correcting codes is not a solved problem, but in this paper that I was referencing, we want to go beyond error correction and talk about fault tolerance. So while these error correcting codes tell you how to correct errors that occur sort of in between these blocks, in practice, what happens if an error occurs sometime within one of these blocks? So within syndrome computation, within the error correction itself, or within a logical operator. So the solution, using a lot of good math, which I will not get into, is that we implement each of these sort of blocks as some fault-tolerant gadgets, which are sort of enforce the property that we're able to still detect and correct those errors sort of after the execution of the gadget. So for the purposes of verification, though, this presents a problem or a challenge, because now these fault-tolerant gadgets themselves don't fit directly into the stabilizer framework. So they will include things like potentially unbounded loops, like repeat until success loops, and classically controlled variables. So verifying the fault tolerance of gadgets takes some additional steps. So first task, formalize actually what fault tolerance means in a way that is suitable to checking, so formally enough to sort of express that property. Now, you could try to verify those properties like manually in Rock, so it's sort of in the style of Squire. But in this work, we aim to reuse as much of like the automated advantages obtained by the stabilizer formalism verification as we could. So our approach was to use symbolic execution of circuits with added symbolic quantum faults. So anywhere that a quantum fault could occur, anywhere that an error could occur, we add like a symbolic error. And then you add a bound that says the total error in the circuit is going to be limited by some bound. The paper has special cases for symbolic execution rules for repeat until success. So you can't just unroll this loop, of course, indefinitely. So you need to have some kind of structure, some kind of guidance into what it means to symbolically execute a repeat until success loop. And as an additional case study within this paper, we talk about magic state distillation, which is a protocol that builds upon fault-tolerant primitives in order to produce certain states in a fault-tolerant way. Okay, so I'm gonna start wrapping up. I want to summarize some of the open problems that we've talked about in this talk. So open problem number 1, we talked about the structures. How do we efficiently represent quantum semantics in a way that's sort of well suited to formal verification? Open problem number 2. We talked about how do we actually verify more than just circuits, but verify quantum programs that have all of the useful programming features that we can dream up. Problem number 3 is sort of the trade-off, the usual story of the trade-off between more automation versus more control over the things that we're verifying. 4, how do we actually express quantum specifications? I didn't get into this question as much, but it's a really, really interesting question. And then 5, verification in the presence of errors. I'm going to bring up one more open problem, which is how do we encourage adoption? This is, always a challenge, especially for domain-specific verification problems. What I've seen from the quantum computing space is that successful verification projects, successful programming language projects as well, can never come just from the classical verification world. They always have to build up from the mathematical foundations of quantum computing to like really make the biggest impact. And so, the best way of doing that is to build collaborations, to build really deep collaborations between formalization experts and domain experts. And that's not easy, right? There's like real differences in motivation, what people care about. There's these language barriers, right? That really do show up when having conversations across domain boundaries. But bridging that gap is extremely rewarding, and I definitely encourage people to try it. So I'm, I think, a little bit early on time, but that's all I have. So I'm happy to take some questions.
We have time for questions.
Thank you for the talk. In your list of open questions, most of them you could replace quantum by classical and it would still make sense. But there is one that I don't see in this list. It's the issue of scaling. Is it because you don't care about scaling to larger circuits or things like that? Or is it not yet relevant? Or?
No, it's definitely relevant. Yeah. No, absolutely relevant. I mean, I was a little bit thinking of that in terms of the problem number one, but of course it's a different problem. We especially care about scaling in quantum computing because we cannot simulate. You can't run classical tests on large quantum circuits, and so whether that's doing the verification on concrete large circuits in some scalable way, or whether that's like reasoning symbolically, like in the example in Rock that I showed, it's extremely important to keep that in mind. Yeah, thank you.
I actually had a clarification question, possibly naive. At some point, I thought you said that when you use these poly tableaus and stabilizers, that you could simulate with just a quadratic number of bits. Is that for a certain class of quantum programs? Or?
Yes. Yes.
And which class is that?
Stabilizer programs. So in the purely unitary fragment, that's Clifford's. But you can also add measurement, and you're still able to classically simulate it.
And so what kinds of programs would fall outside this class? So the Clifford class makes up like a very large percentage of basically every quantum algorithm, but most of the sort of introductory algorithms will have other things as well. So like a universal quantum gate set, one common universal quantum gate set is like Clifford plus the T gate. So T is a gate that is not Clifford, and just by adding that one gate, you can sort of expand the Clifford set into all to a universal quantum set, so any possible unitary. That's also true of like, instead of the T gate, an arbitrary rotation around the any particular axis, like a Z rotation. There's definitely a lot, yeah. Right, thank you.
A lot more other people could say.
So you described the possibility to scale reasoning because of having parameters as we are used to see in classical verification. And you also said that simulation, especially with the first representation, was not practical because even the floating point numbers are not big enough to get the precision you need. But you might still consider having simulations for the small examples and then scaling up using the induction capabilities. Is this something that is this a line of research that is really active right now in the domain?
Yeah, absolutely. I think that the line of research in ROC, sort of following this Squire type of work, that's generally the approach. Is you're reasoning by induction, and the base cases you'll sort of use tactics that will
you can use
do the
brute
simulation.
force for the base cases.
Yeah. Mm-hmm.
And
well, because in ROC you can reason about, you can use actual complex numbers rather than approximate, right? And then induction to get sort of all of the cases. So that's definitely a popular technique. Yeah.
But you can also even use floating point expansions and things like that to increase your precision if need be.
Yeah. Mm-hmm. And people do simulations using floating point numbers. That's absolutely absolutely what people do in practice. Yeah.
Thank you for the very nice talk. The slide of yours here lists some open problems at an abstract level. Is it possible to give an example of a program that you would consider out of reach with respect to this current state-of-the-art of verification techniques in terms of, I don't know, features or size or whatever?
Yeah, that's a great question. I believe that I don't necessarily think that there's any algorithms that are like conceptually out of reach. If we're doing like in terms of functional correctness, I mean, in terms of if you're using an automated technique, then certainly some approaches will work, up to a certain size and then will time out. If you spend a long time doing like formal verification in ROC, I think you can definitely push it, as far as you want, given given how much time you want to spend on it. I think that especially when you're, I don't really know the current state of the art, especially when we're talking about like some of the more probabilistic or approximate algorithms. That might be something that is not fully explored yet, but yeah.
We still have time for another question. If not, let's thank Jennifer.
Thank you.